Welcome back to the deep dive. If you're looking to efficiently get up to speed on cutting-edge machine learning research, you're in the right place.
That's the goal.
Today, we're tackling a really interesting paper. It dives into a pretty complex optimization problem.
Yeah, finding the best routes when you're juggling multiple criteria simultaneously.
Exactly. Like not just the shortest path, but maybe the fastest or the one using the least fuel all at once.
It's called the multi-objective shortest path problem, MOSP for short.
And this paper, it proposes a new way to solve it using parallelized A search.
Which is pretty neat and highly relevant, I'd say.
Oh, definitely. I mean, this isn't just theory, is it? Think about robot path planning.
Right, or UAV route selection, even optimizing how planes move around on the ground at an airport.
All those situations where you have competing factors, time, fuel, maybe even emissions.
Absolutely. And finding efficient solutions for MOSP, well, that has some serious real-world implications.
But the existing methods, things like multi-objective A or MOA, they have limitations, right? Especially as you add more objective.
We do. Performance can degrade quite a bit. And interestingly, even the order in which you consider the objectives can have a big impact. It's a known challenge.
Like trying to optimize too many things at once just bogs it down.
Pretty much. So
Yeah.
the core idea in this paper, the main contribution, is this novel parallel framework.
Okay.
They run multiple MOA searches at the same time, but each one uses a different objective ordering.
And they've got a special trick to make it efficient.
Yeah, a unique upper bounding strategy. That's really the key to coordinating these parallel searches and getting that performance boost.
Okay, let's maybe unpack the basics first.
Mhm.
The paper focuses on finding Pareto optimal paths. What exactly does that mean in this context?
Good question. Think of it like making a trade-off. A path is Pareto optimal if you can't find another path that's better in one objective, say, faster,
Okay.
without it being worse in at least one other objective, like using more fuel.
So there's no single best path necessarily. It's a set of the best compromises.
Exactly. MOSP aims to find that whole set of non-dominated best compromise solutions. You can't improve one aspect without sacrificing another.
Got it. And MOA is the tool for this. How does it take the classic A search idea and apply it here?
Well, like standard A, it uses a heuristic, an estimate, to guide the search. But instead of a single cost estimate,
Use multiple, a vector.
right, a vector of costs, one for each objective. So fx(x) plus hsx becomes a vector equation. Gx is the known cost vector to node x, and hsx is the estimated cost vector from x to the goal.
And it uses that to decide which paths to explore.
Yep. It keeps potential paths in a priority queue, usually called the open set, ordered based on these cost vectors, and it stores found solutions in a sol set.
The paper also mentions this GTR list. What's its role? It stores non-dominated truncated cost vectors. Sounds complex.
It's a clever optimization. GTR stands for goal truncated. For each node, it stores the best cost vectors found so far to reach that node, but it temporarily ignores the first cost component in the vector when comparing.
Why ignore the first one? Let's say the order is time, fuel, emissions. You ignore time.
Precisely, because MOA often sorts paths primarily by that first objective, time, in your example. When you arrive at a node via a new path, you can quickly check its secondary costs, fuel, emissions, against the best secondary costs already stored in GTR for that node.
So if a previous path got there with better or equal fuel and better or equal emissions, this new path isn't likely to lead to a better overall Pareto solution, even if its time is slightly different.
Exactly. It's a quick pruning check using that TR operator, as they call it. It lets you focus on whether the path offers a better trade-off on the other objectives.
Okay. And then there are specific MOA variants like LTM.O.A and NWM.O.A. What's the difference there?
They're basically refinements of the core MOA idea, represented the state of the art before this paper. They differ in mainly two things: how they order nodes in the open list and how they perform dominance checking.
How so?
LTM.O.A uses a strict lexicographical order, like a dictionary, sorting across all objectives. NWM.O.A prioritizes the first objective more heavily. For dominance checking, LTM.O.A compares against all previously found solutions, while NWM.O.A uses a more structured approach, sometimes involving sorting, and includes a quick pruning check based on recently found solutions.
So different trade-offs in how they manage the search.
Right. Different ways to try and speed things up.
All right, so that sets the stage. Now let's get back to this paper's main idea, the parallel MOA framework, running multiple searches.
Yeah.
How does that work?
It's conceptually pretty neat. For, say, K objectives, they launch K instances of an MOA algorithm, like NWM.O.A, in parallel. But the key is, each instance uses a different objective priority. They typically use cyclic permutations. So instance 1 might prioritize objective 1, then 2, then 3. Instance 2 prioritizes 2, then 3, then 1, and so on.
Attacking the problem from different angles simultaneously.
Exactly. And they note this seems to be the first real attempt to parallelize MOA effectively for more than just two objectives.
But why is upper bounding so critical here? Why not just let them run?
Because of redundancy. Without coordination, these parallel searches could waste a lot of time exploring the same or similar suboptimal parts of the search space. The overhead could outweigh the benefits of parallelization.
You need them to share information.
Precisely. Upper bounding is the mechanism for that. It allows one search thread to find a good solution and communicate bounds based on that solution to the other threads.
Okay, how does that communication work? How does the, say, time-focused search use info from the fuel-focused search?
This is their novel contribution. Let's say thread 1, prioritizing cost F1, finds a solution with costs F1, F2, Fk. It can immediately tell the other threads, any path you're exploring that isn't better than F2, Fk on those remaining objectives probably isn't worth pursuing from my perspective.
That's the basic idea of pruning using found solutions. What's the extra step here?
They add another layer. Thread 1 can also look at the progress of, say, thread 2, prioritizing F2. If thread 2 has explored paths up to a certain cost F2, and thread 1 finds a solution where its own F2 is less than or equal to F2.
Meaning thread 2 has likely covered that region of fuel costs.
Right. Then thread 1 can potentially tighten its pruning even further. It might be able to prune paths based on just F3, Fk compared to the solution it found, effectively using thread 2's progress to reduce the dimensionality of its own checks.
And they can chain this across multiple threads.
Yes. By doing this K1 times, considering the progress across threads, they can reduce the check down to a single scalar comparison on the kth objective. It provides a very tight, constant time, upper bound check for newly expanded nodes.
Wow, okay. That sounds efficient.
It's designed to be. They also maintain a global upper bound vector, let's call it F-bar, which stores the best cost found so far by any thread for each individual objective.
And how does that help?
Any thread can use this global F-bar to prune. If a thread is exploring a path and its cost for objective out already exceeds the global best F-bar, it can potentially discard that path immediately.
Because it can't possibly be Pareto optimal globally.
Exactly. It also enables early termination. If a thread realizes its primary objective cost is already worse than the global best for that objective, it might stop searching altogether.
So they had to modify the MOA algorithm itself to use this. You mentioned the GTR list earlier. How did that change?
Instead of a single GTR list, they now use a list of sets, GTR1, GTRK1.
Yeah.
GTRJ stores truncated cost vectors, where the first J components have been notionally hidden or truncated.
To support those multi-level checks you described.
Precisely. It allows them to efficiently store and query the bounds needed for those progressively tighter dominance checks.
And the check itself is done by this dominated MD procedure, algorithm 4.
Right. MD for multidimensional. When checking a new node's cost vector, it first compares against the global upper bound F-bar. If it passes that, it then checks against the cost stored in GTR1, one component truncated, then GTR2, two truncated, and so on. It's the layered filtering process.
And what about update upper bound algorithm 5? When does that come into play?
That gets triggered whenever any thread finds a new non-dominated solution that makes it into the main sol set. It then checks if this new solution allows tightening the bounds stored in the GTR sets. It looks at the truncated costs stored at the goal node. If the new solution dominates some previously stored truncated cost vectors, considering the progress of other threads, those old vectors are removed.
And potentially replaced.
Yes, potentially more aggressively truncated versions with more components hidden might be generated and added to the next level GTR set, like moving from GTRJ to GTRJ plus 1, and the global F-bar vectors updated if the new solution improves any component. It's how the shared knowledge gets refined.
The example in Table 1 really helps visualize that chain of truncations.
It does. It shows how you can start with a 4-objective vector and, by comparing against other solutions in progress, effectively boil it down to a single scalar bound for pruning. Much more powerful than just single truncation.
And after all this parallel searching and bounding, there's a final merge step.
Yeah, just a final cleanup. Although the upper bounding drastically reduces redundant work, it's still possible for different threads to independently find the exact same Pareto optimal path. So they collect all solutions from all threads and remove duplicates to get the final, unique Pareto set.
Makes sense. And they provide theoretical guarantees, lemmas and a theorem.
Yes, which is important. Lemma 1 basically says the multidimensional truncation pruning is correct. It won't mistakenly throw away actual Pareto solutions. Lemma 2 confirms that the derived bounds are valid globally across all threads.
And theorem 1.
That pulls it together, stating that the whole parallel framework using these procedures correctly finds the complete set of Pareto optimal paths for the MOSP. It establishes the soundness of the approach.
Okay, theory is solid. What about the experiments? They tested this on a New York City map.
They did. Using road network data with 3, 4, and even 5 cost components, things like distance, travel time, maybe tolls or elevation changes.
And the results.
Pretty compelling. First, the parallel approach consistently solved more instances, especially the harder ones with more objectives, within the time limit.
That's a good sign.
Second, significant runtime improvements. They saw speedups roughly proportional to the number of objectives, sometimes up to an order of magnitude faster than the sequential state of the art.
Wow. Any downsides?
Well, as expected with parallelization, memory usage increased because you're running multiple searches. But the key finding was that their parallel method with the upper bounding significantly beat a version without it.
So the bounding is crucial.
Absolutely. It even beat a theoretical oracle approach that magically knew the single best objective ordering to use beforehand. This really highlights how effective their cooperative bounding strategy is.
Did they try just switching the order sequentially?
They did try a sequential alternating search order, and it only gave marginal improvements. It really shows the benefit comes from the parallel execution combined with the information sharing.
Interesting. So placing this in the broader research context, where does it fit what came before?
Well, people have been working on multi-objective search for a while. Early work focused a lot on bi-objective problems. Heuristic search, like A, really pushed MOA forward.
With algorithms like the LTM.O.A and NWM.O.A we discussed.
Exactly. Those were key steps. But parallelizing search itself, while common for single objective problems, hadn't been explored much for multi-objective search beyond 2 objectives. There was an algorithm called B.O.A for bi-objective, but this paper tackles the K2 case.
And it tackles that known issue of objective ordering sensitivity.
Yes, that dramatic effect mentioned in prior work. By running multiple orders in parallel and sharing info, they effectively mitigate the risk of getting stuck with a single bad ordering.
Okay, so let's boil it down. What are the absolute core takeaways here?
I'd say, 1, the main innovation is running MOA in parallel with different objective priorities. 2, the critical enabler is the novel multidimensional upper bounding technique that lets these parallel threads cooperate effectively.
Cutting down redundant work.
Right. 3, this leads to potentially huge reductions in computation time for complex MOSP problems, especially with many objectives.
Yeah.
And 4, the experiments strongly back this up.
And the real-world impact. Why should someone outside academia care?
Because faster MOSP solvers mean better, quicker solutions in all those areas we mentioned earlier. Think real-time autonomous navigation that needs to balance speed, energy, safety.
Or logistics planning, finding routes that optimize cost, time, and maybe risk for carbon footprint.
Exactly. Better algorithms can lead to more efficient operations, smarter autonomous systems, and potentially better decision-making whenever multiple criteria are involved in pathfinding.
All right, great summary. Now let's shift gears to our novel notions segment. Where could this research lead next? What new ideas does it spark?
Okay, one thought. The current paper uses a fixed cyclic permutation of objectives for the parallel threads. What if that could be dynamic?
Dynamic objective ordering. How would that work?
Imagine a system monitoring each thread's progress. If one objective ordering, say prioritizing fuel first, seems to be finding Pareto solutions much faster, or contributing more effectively to tightening the global bounds.
You'd give it more resources, more compute threads.
Potentially, yeah. Or maybe you dynamically shift other threads to explore variations around that seemingly successful ordering. You could almost frame it as a resource allocation problem.
Like a reinforcement learning agent deciding how to assign threads.
That's an interesting angle. The agent could learn which orderings are most promising for a given problem instance, or even during the search itself, based on metrics like Pareto front discovery rate or upper bound improvement.
That could really adapt the search on the fly, especially for time-critical stuff.
Exactly. Emergency response, dynamic fleet management, getting good multi-objective solutions faster could be huge.
Cool idea. What else?
Another area is heuristics. The paper uses traditional A heuristics. But we know machine learning, especially things like graph neural networks, GNNs, is getting really good at learning heuristics.
So integrate learned heuristics into this parallel framework.
Right. The obvious benefit is that better heuristics usually mean fewer node expansions, speeding things up further.
Makes sense. Is there a less obvious angle?
Well, maybe you could train different learned heuristics, each specialized for a specific primary objective. So the thread prioritizing time uses a time-focused learned heuristic. The fuel thread uses a fuel-focused one.
Tailored guidance for each parallel search.
Precisely. And maybe, just maybe, the upper bounding mechanism itself could provide feedback to help refine those learning heuristics over time or across different problems. You can potentially use meta-learning ideas here.
Learning how to learn the best heuristics for different multi-objective scenarios. Interesting.
Yeah, building on recent work in single-objective learned heuristics and extending it.
These are definitely thought-provoking directions.
Of course, just speculative ideas for, entertainment and discussion. Future research always surprises.
Absolutely, but it really shows the richness of this paper. It's not just a solution, but a potential starting point for more innovation. So the key takeaway for listeners is that this research offers a significant step forward for solving the multi-objective shortest path problem efficiently.
Through Parallel, a search combined with that clever upper bounding.
With real potential to impact applications needing multi-criteria optimization. If you want all the technical details, the paper link is in the description.
Definitely worth a read if you're into optimization or pathfinding algorithms.
And we'll leave you with a final question to ponder. Beyond shortest paths, how could these ideas, parallel exploration, shared upper bounding, maybe even dynamic adaptation, be applied to other complex optimization problems in machine learning where you're juggling multiple conflicting goals?
Food for thought. Until next time on The Deep Dive, keep exploring.